So today we're going to switch gears a little bit. I'm going to start talking about some geometric things that are important. And the first of which we've actually kind of seen before. It has been important. It's been used when we dealt with distributed loads. So when we did those rectangles and triangles, we always put them at their centroids. And so we're going to delve a little more into that topic today, then the next couple of days do some other geometry related topics. And so for today, I'm going to deal with centers of mass or centers of gravity and centroids. So in general, those are not necessarily the same thing. So center of gravity or center of mass, those two things are the same thing. That's kind of where all the weight could be held. So again, if I have some sort of pencil, if I find exactly where this thing's going to balance, there we go. So that is the center of mass, or that's the center of gravity for my pencil. And that's generally where we can put things like weight. So usually when we had boxes and things, we just put weight right in the middle. But technically what we're doing is we're putting it at the center of mass or center of gravity. So that's generally where the weight should go. As opposed to that is the centroid. So the centroid doesn't worry about balance, anything like that. Centroid is purely geometric. Centroid is just where is the center. So you may have noticed on my pencil, center of mass wasn't exactly at the center. But the centroid is the geometric center. Now, a lot of times they're both denoted by the same thing. So in this textbook, it's called X bar, Y bar, and Z bar, and that's for both the center of gravity and the centroid. The reason why it's usually the same variable is generally in these sort of textbooks and these sort of introductory classes, most materials we deal with are homogeneous. So every box we've dealt with, we've assumed it's completely uniform. So all the weight in there is distributed evenly. If that's the case, then the center of gravity and the centroid are actually the same point. So a lot of times in this class, in fact, all times in this class, center of gravity and centroid will be the same thing because we'll be dealing with homogeneous items that we're assuming the density is distributed evenly throughout the entire thing. In real life, that may not be the case. Best example of that is something like a hammer. Hammer has a steel head, which is really heavy, wooden handle, which is relatively lighter. And so the center of gravity will be closer to that steel head as opposed to the centroid, which again, only volume is wherever the center of that hammer is geometrically. If we're dealing with a single material, something like a 2x4 piece of wood, there are some slight variations in that. There's things like knots and other inhomogeneities, which actually alter the density slightly. But usually those are small enough that we don't worry about them. And that's why we usually make this assumption that the center of gravity and centroid are the same thing because the material is homogeneous or close enough. So again, we've already seen two of these. We've seen rectangles and triangles. And so for the rectangle, centroid or center of mass is right in the middle. In this kind of coordinate system I laid out here with the rectangle over there, I have center L over 2 in the x direction, center Y over 2 in the, center H over 2 in the Y direction. So there's my centroid for the rectangle. For a right triangle, again, we've seen these before. The centroid was 1/3 from the big side. So again, the way I've drawn this one, 1/3 from the big side in the x direction. The big side is way over here. So I have to come in 1/3 L, which gives me 2/3 L from the point up here. So from the origin, I go 2/3 L. So 2L over 3 is my x coordinate. So again, if this triangle was oriented kind of the other way, if it's oriented like this, then it'd be L over 3 to the centroid, like we usually call it. Just like Y, big sides on the x-axis, so it go up H over 3 to find that centroid. So those are two relatively simple shapes, actually the two simplest shapes, really. So really what we want to do now is look at more complicated shapes. So we did see way back when we did these distributed loads that there is an integral way to do it. And so that is one option. If I have a more complicated shape, I could use those same integral formulas that we saw before. There's another option though, and that's decomposing shapes into shapes with known centroids. So we've seen two basic shapes. Those are rectangles and triangles. There's a few other ones, and those are generally given in figures. So this textbook has figure 5.8, page 239, 240. They're also going to be shown later here. And what we can do with those is we can kind of build more complicated shapes out of these basic shapes. So I can take a whole bunch of rectangles and make a kind of more complicated shape that's can be decomposed into a whole bunch of rectangles. And then I can use the centroids of rectangles, which I know, and use that in a certain way to add things up. So first option, the integral formulas. So specifically for center of mass, I'm looking at the mass of the object. So just like we did before, I want to take make sure the moments balance. So moments in terms of x times dm, x bar for the entire thing times m equals those two, or equals that integral. And so to find x bar, I just divide by m. And then m is usually written as the integral over dm. So integral of dm, some small element of mass, integrate that over the entire mass, and I just get the mass. But it's usually written like this. But this denominator is just the total mass m. And so to find my x coordinate of the centroid, just integrate x times dm over my entire object, divide that by the total mass. That gives me the x coordinate. Similarly for the y coordinate, y times dm integrated, and similarly for the z coordinate. So those are the three coordinates, x, y, and z, of my center of mass or center of gravity. Centroid is a slightly different definition because, again, centroid, I only care about the actual geometric center. So in this case, I only care about the volume. I don't care about how the mass is distributed. I just care what the object looks like. So in terms of volume, but very similar formula. Instead of integrating over mass, just integrate over volume. So dv instead of dm. Again, I have the integral of dv on the bottom, which again is just total volume v. And I do that for the x coordinate, y coordinate, and z coordinate. Then we can see here mass and volume are related to the density. So density is mass divided by volume, which means that if I rearrange this, mass is density times volume. So dm is density times d volume. And then we can see here if density is constant, basically I can just take the previous formulas with dm, replace it with rho dv, and then they'll have a rho up here, a rho down there, and because it's constant, they'll cancel out. So as long as density is constant, x bar, y bar, and z bar using volume gives me the exact same answer as x bar, y bar, and z bar using mass, indicating that the centroid and center mass are the same point. Again, if rho is constant for homogeneous items. Now, those are the official three-dimensional versions. There's also equivalent two-dimensional versions. So again, when we dealt with the rectangle and triangle, that was technically a two-dimensional rectangle and a two-dimensional triangle. So in that case, instead of integrating over the entire volume, we only have to integrate over area. There's no variation in the z direction. So dA, basically dx times dy. So integrate over x and y directions. Again, have a total area integral of dA on the bottom. And so that gives me x bar and y bar, the locations of the centroids. There's also certain cases where we want to find the centroid of a line. So line being basically one-dimensional. So now instead of dA, we're down to dl. So the centroid of a line, integral of x dl over integral of dl. Again, bottom is just the same as the total length L. So that's the integral method. The other method is, again, taking all these basic shapes and breaking them down, or then constructing a more complicated shape out of them, or on the other hand, having a complicated shape and being able to break it down into these basic shapes. So again, we saw rectangles. Rectangles didn't even make this table. I guess they're too easy. But then we also have triangles, and these are not specifically right triangles that we saw before. This is kind of a more complicated triangle. But again, I have an x bar and a y bar that I can find from my triangle. Quarter circles or semicircles, quarter ellipses, parabolic areas, The other part of the parabola, so this is kind of the upper part. This is kind of under the parabola. And then some other general equations, sector of a circle. So some part of a circle, not necessarily half of it. Again, have some x bar and y bar coordinates of the centroids. And then have some one-dimensional shapes. So just the line in terms of a semicircle, or just a line in terms of a circle. I have the centroids of those as well. So based on all these shapes, triangles, rectangles, circles, whatever it is, if I can build another object out of all these shapes, one way to find the centroid of the entire shape is to actually take kind of all the individual components of the centroids and add them all together in a certain way. So these more complicated bodies that I can make out of smaller bodies are called composite bodies. I basically composed them of a bunch of different littler shapes. So what we officially did for the integration part is we've kind of integrated over each tiny little point. So I had some infinitesimal points on my volume or area or mass, whatever it was, and I integrated all those tiny little points. This is more integrating really big areas. And so in that case, my integration becomes a sum. So I just take essentially the centroid of each individual shape. So each individual rectangle has its own x bar centroid. And we call that x tilde for all the individual tiny little shapes. X bar will be for the overall shape. So each little rectangle, sphere, not sphere, circle, triangle, whatever it is, has some x value as centroid, has some mass associated with it, or volume or area, whatever I'm dealing with. And so I take each of those for each rectangle, x tilde times delta m, x tilde times delta n, add them all up, and that kind of gives me an overall x tilde times delta m. And then I divide that by, again, the total mass. So each individual object has some mass delta m, add all those together, get the total mass. So essentially I take centroid value times the mass of each individual object, add all those together, and then divide by the total mass, and that gives me the total centroid value for both x, y, and z. And so again, this is whether I'm dealing with center of gravity, I use delta m. If I want just centroid, I'm using either delta v or delta a or even delta l. Whichever situation I'm dealing with, I just take, again, each individual centroid value times its mass volume area, add all those up, divide by the total mass volume area, and that gives me the total centroid value. So this is probably something that will be easier to see when you actually do examples of it. Going through examples will probably be a lot easier to see. So later today in class, we'll see some of those and hopefully makes this a lot clearer.